This is off of 1.3b. We did conjugate practice. We did common denominator practice, or introduction and review. But we haven't done squeeze theorem. So let me spend a minute just going over squeeze theorem. It's an easy concept. I just want to go through an example with you, make sure those make sense. And then we will do review. And then for review, I want you guys to do the 1.2, 1.3 review from Friday that we didn't get to, and either let you guys work in groups. I'm going to have you guys go into the separate rooms if you want to work in groups, or you can work individually, or you can stay in the main room and ask me questions. But yeah, that's the plan for today. So let's talk about squeeze theorem. Let's say we had three graphs. Okay, there's the lower graph, the F. There's the middle graph, which is the G, and let's say there's the upper graph, which is the H. And by lower, middle, and upper, what I mean by that is location. That F is always going to have the Y values at any point of the. If we compare the, if we just draw a vertical line down any point, F is always going to be the lowest, G is the middle, and H is going to be the highest. So in the graph below, the lower and upper functions have the same limit at x equals a. So the idea is that if we're looking for information, if we're trying to solve for a limit of the middle function and we don't know enough information about the middle function, but we do know that but we can establish a relationship between the middle, between two separate graphs, then the hope is that if we have enough information about the lower and upper function, if we can get these two to match with the same limit, then we know this g of x must also be that limit as well. So we're able to use some surrounding relationships to help us figure out kind of an indirect way to figure out the limit, especially on problems where we don't have enough information about the middle function. Okay, let me go to a clean copy here. So, so graphically, what we're trying to do is this. Graphically, we're trying to show that F and H are going to meet up at the same Y value. If they meet up at the same Y value, then G is going to get squeezed between them, and it must have that same value as well. So let's say the problem is always, okay, so if we want to do squeeze theorem, the problem has to establish a relationship for us between three separate functions. So here's example 3. We have the relationship established for us. F is always less than or equal to G, and G is always less than or equal to H. We want to find the limit as x approaches 0 for g of x, but we don't know the function for g of x, but we're going to rely on the others to help us out. So I'm going to just say that I want to find the limit for each of these three, and I'll leave the inequalities there as well. Now we have a substitution that we can make between the F and the H, right? Because we have information about that. So I'm going to make a substitution so that I can evaluate those two pieces. F is the x squared plus 1. And then the H is going to be just 1, so So I'm just going to evaluate these because I can actually plug something in, right? I have something to plug in. Here I don't have anything to plug in, but here I do. So if I plug 0 in for x, I get 0 plus 1. Here, if I plug 0 in for 1, there's no variable, so that 1 is going to stay a 1. So this is my resulting limit. Because my upper and lower are in agreement, I know my middle one must also be in agreement as well. So based off of this, we can conclude by squeeze theorem the middle limit must also be equal to 1. Okay, so that's all there is to squeeze theorem. You evaluate the lower, you evaluate the upper, see if they're the same. If they're the same, then we can conclude what's happening with the middle limit. Okay, any questions about the process that we went through? So let me ask you, what if these are not the same? What if one was showing 1 and the other is showing 3? Can we make any type of a conclusion?
Does not exist.
Okay, maybe not does not exist, but just inconclusive. How's that? Yeah, because if it was 1 and 3, we know limit is somewhere between 1 and 3, but we don't, right? We only have a range. We don't know the exact value. So I would say if they don't agree, then you would just say the limit as x approaches 0 of g of x is inconclusive. Not enough information. Maybe the limit does exist. We just don't know, at least not with this method. Not enough info. Right, so either they're in agreement and we can figure out the value, or they're not in agreement and it's inconclusive, or we don't know. We still, our conclusion is still undecided. Okay, any questions with squeeze theorem? Okay, that's really the only new material I want to go over today. Let's look at the review, or the review from Friday that I didn't get to. And I just want to run through a couple of big ideas, and then you guys can work individually or work in small groups. So if we want to find the limit or order pairs off of a graph, then order pairs are easy. You're just looking for the x, you're just looking for the y value at that point. But if we want to find the limit, what you want to do is you want to locate that target that you're considering, and then you want to plot 2 points on either side of that target, and then you're going to draw arrows towards that x value along the path. And if your arrows are pointing to the same y value, then you know that, or if the arrows are eventually going to meet, except for that hole or that order pair, you know that's where your limit is. Okay. Now, if on opposite ends of your x value, you plot points and the arrows are obviously pointing or moving towards a different location or a different destination, then you know the limit does not exist. Another place where limit doesn't exist will be vertical asymptotes. So when you see a vertical asymptote, you're going to say limit doesn't exist, but then you're going to try to provide a subcategory if you can. If the arrows are pointing in the same direction, then you would say limit doesn't exist, and then either positive infinity if both are going up, or negative infinity if both are going down. But if one's going up, the other's going down, then there's no subcategory. You just say limit doesn't exist. Right. Now, the more challenging one are the ones where you have to take properties and put it onto a graph. So what I would do is I would start with ordered pairs first. I think those are the easiest ones to put down on paper. And then you want to move on to the limits. So if a limit exists, then you want to plot a hole at that point and then extend the graph on either side of that hole to ensure that the graph is going to have a limit. The only addition you may have to make with that graph is you may have to fill in that hole. But if you fill in that hole, there's going to be another property that tells you to fill in that hole. Okay. So I think the safer route to go is to start with the hole, extend from both sides, and a lot of times you can leave that alone. You're never going to have to erase anything. The most you may have to do is to fill that hole in if another order pair is defined there. And then the last is this very broad statement, limit doesn't exist. If a limit doesn't exist, you have three options. Either you make the graph an endpoint at that location. You can make it two disconnected lines to that x value, or you can make it a vertical asymptote. So everyone's graph may look a little different. Yours may not look the same as mine on my key, but just know that you have a variety of ways to show or to demonstrate limit doesn't exist. Okay, any questions about first page? Another thing is I want this to be a function. So I think the biggest mistake I see students make is with their arrows. Make sure that you don't have arrows that are pointing to, in opposite direction. If you have arrows pointing in the opposite direction, this is going to cause an issue because no matter how I follow those lines, they're going to either overlap or they're going to cross each other, and that's going to cause eventually two overlapping lines. Okay. So if you want to draw arrows, you can draw arrows exiting the graph. That won't cause any issues. Or you can have asymptotes. So the only time that you're going to have any arrows is if they're pointing, exiting the graph, or they're pointing along a vertical asymptote. But we should never have arrows pointing towards the graph. That's going to cause an issue with not passing the vertical line test. Now the back page are all going to be limits algebraically. So evaluating limits algebraically, let me run through your steps. The first thing we always do is we plug in that argument. We plug in that x value. The reason why we do that is we want to have some idea, some foundation to build off of, right? We want to know, is the graph continuous? If it's continuous, then whatever number we get, then that's our answer. Is it a vertical asymptote? If it's a vertical asymptote, it'll give us 10 over 0 or 8 over 0. Then we know a limit doesn't exist. Is it a hole in the graph? If there's a hole in the graph, then we'll get 0 over 0. And if we get 0 over 0, we know there's a limit exists. There's an answer at the end of this process. We just have to go through our cleanup steps to get there. And what I mean by cleanup steps is when you see 0 over 0, you're going to look at the problem and you're going to decide which of these methods to apply. Is it just the factoring problem, where you can factor and then find a common between numerator and denominator and then cancel out? Is it a radical problem where you got to involve the conjugate? Is it a complex fraction where you have to involve common denominators? Either way, the goal is the same. You're trying to find the hole to match between numerator and denominator so that you can cancel out. So a couple of things I want to point out. If you look at the key, the way I worked through the complex fraction problem is I found the common factors and I distributed that through. But this year I'm trying to just to go through common denominator method just to see if it's more straightforward. So if you want me to go through number 3, you can kind of stick around I can go into your rooms and show you if you're having trouble with this one and the key doesn't make sense. Okay, so just I want to make sure that that if you're going through the method that you're being supported, if you're struggling with that. The other thing I want to point out is number 7, okay, is that my key is incorrect. It should show 18 and not 9. So if you guys can just make a note, the answer should be 18. And the mistake that I made with 7 was I jumped into star method, Lizzie method before my first step. I should have taken GCF out first. So if you don't take the GCF out first, your factoring is going to be off, more likely than not. So if there's a GCF, you got to take that out first, and then you can look inside the parentheses, and then you can decide whatever factoring method you want to use. But the first step is always GCF. There may not be a GCF, but if we look for one, if there is one, that has to come out first. So because I didn't do that, that caused my answer to be off. So it should be 18. And again, if you need me to go through factoring, I can go through that with you, either here or in the separate rooms. Okay, any questions before we break? Okay, so you're feel free to work individually if you like. You can stay here. I can go over problems. You can go into the rooms. I'm going to start opening up the rooms. So I'm going to start with room 1. Once somebody is there, then I'll open up room 2, and then you guys can decide which rooms you want to be in. So it's up to you. Okay. And then once you guys are in rooms, I'll just kind of visit. I'll just make my rounds and see if you guys have any questions within each of the rooms. All right, let's see. Okay, back in the main room, is there any room that you're trying to get into but couldn't, or if you want to prefer to stay here, that's fine. Or if you want to work individually, logging off this call, that's fine as well. But yeah.
How do you join a group?
I think you can just go back to, let me see if I can share my screen. You can just go to the fourth period, and then you should be able to, if there's a hidden channel, you can click on the hidden channel, and then you can just go into any of the rooms that you want to join in. I think if you just click on it, you should be able to hit join, and then it'll take you into that room.
All right, thank you.
Yeah, I have the first 4 rooms open, but anybody want to open the 5th or 6th room, let me know. Okay, so I'll stay in the main room for now. Let me know if you have any questions. You want me to go over anything? You want me to show the key for any specific problem? Okay, I'll come back to the main room. I'm going to see how the other groups are doing. Okay, any questions? Any problems you want me to do in detail? Any key that you want to check, or any problems you want to check with the key? Yeah, number 7, all right. So here's how we start with number 7. First thing we do is we have to see where we're at, right? Kind of gain some perspective as to how to move forward. So we plug 5 in for the x's, and we get 0 over 0. Let me start with a fresh sheet here. So once we confirm 0 over 0, we know this is going to be a factoring problem. There's a hole that's hiding inside here that we're going to have to identify so that we can cancel out. So the first thing we do is there is a common factor, so we got to take that GCF out. So we can take out a GCF of 2. Okay, so then once we have that common factor of 2, then we can focus our attention with the trinomial inside. And we can ask ourselves, what multiplies to be 10 and adds it to be negative 11? So I go through this star method here. So we're trying to find 2 numbers that multiplies to be 10, a times c. But we also want those 2 numbers to add up to be the middle term, which is negative 11. We stick our a value in these below spaces here. So now it's a bit of a puzzle. We ask ourselves, what can multiply to be 10 and adds up to be negative 11? So if you think about factors of 10, we have 1 and 10, we have 2 and 5. So we want 2 numbers to add up to be 10, but multiply to be 10 and add to be negative 11. The only one that's going to get even close to 11 is going to be 1 and 10, right? Because we can't add 2 and 5 no matter how you combine, whether you make it positive or negative. We can get 7, we can get 3, but we can't get 11. But 1 and 10 can help us get to 11. So I'm going to pick those 2 numbers, 1 and 10. But I got to play with the signs to see which one works.
Shouldn't the numbers multiply to be 5, not 10?
So here's the thing, though, is that would be the case if my leading coefficient was a 1. But because it's a 2, I have to involve a and c to arrive at the number that I'm trying to multiply to. Normally, yes, I can see how problems where you only look at the third term, but that's if there was no 2 in front. If there was x squared minus 11x plus 5, then you would say, okay, I'm just looking for that c value. But if there's a leading coefficient, we got to do a little bit more work. Does that make sense?
Yeah, I didn't see the 2, sorry.
Yeah, so we need that, yeah. So so that 2 kind of impacts how we do our factoring step. So now we have 1 and 10. I'm going to adjust the signs, though. I want negative 11, so I need both these to be negatives. So double check. This is true. This is true. So we get negative 1 and negative 10. So now we can get closer towards our factored form. X's will always come first. And then we're going to put our fractions here unless we can reduce. So 1/2 doesn't reduce, so we'll do minus 1/2. 10 over 2 reduces to be -5, so now we're almost there. The only thing is, if there's any leftover fractions in the denominator, we want to pull that out in front. Now that we see our common factors appear, we can reevaluate, plug 5 into the remaining x. So we get 10 minus 1, which is 9, so that's how we get 18. Hi, Catherine, to answer your question, or is there any other detail you want me to go over?
No, I'm good.
Okay. Okay, let me know if there's any other problems you want me to work through, or any ones that you're stuck on. Yeah, so my steps on the complex fractions are going to be different than the ones I've been going over with you, so just be aware of that. Oh, number 5, okay. Okay, first things first, we want to plug 2 in. So 2 goes in for x. 18 minus 2 is 16. Root 16 is 4. 4 minus 4 is 0. So we get 0 over 0. So that tells us, okay, we got to find that whole to eliminate, which means I got to go through conjugate process. I see a bunch of radical. I see a radical up top. So here's my conjugate term. It's going to be same as my first terms. The only thing I changed is that sign in between. So this process is going to help us clean up that radical in the numerator. So now we FOIL. But when we FOIL, we only look at the first pair and the second and the last pair. So 4 times 4 is 16. The middle terms will drop out. Don't worry about that. And then we multiply the two radicals together. There's a negative times positive, which is negative. So I want to protect that expression with its own set of parentheses. Denominator, we leave alone. We don't touch the denominator in terms of expanding. We want to leave it. We want this x minus 2 to be visible because that's essentially, eventually this will go away for us. We don't want to lose track of that. So now, if I distribute the negative through, I get 16 minus 8 plus x, and that becomes negative 2 plus x. I know these may look like they're different signs, but they're actually the same signs. The x is positive, the negative 2 is, the 2's are negative. So if I just rearrange it, maybe it becomes more obvious that They're actually the same. There's no opposite signs going on there. So we see common factors. Anytime you cancel common factors and there's nothing left in either the numerator or denominator, keep in mind it's a 1 left over, okay? It's not a 0, it's a 1. So now we have our whole has been removed. We can reevaluate. So plug 2 in for x. 18 minus 2 is 16. Root 16 is 4. 4 plus 4 is 8. And that 8 stays in the denominator. Okay, Samuel, does that answer your question? Okay. Good, let me know if there's anything else. Okay, bell's about to ring. Okay, so I want you guys to be comfortable with all these types of problems so that when we move to the next thing, we can have this as a foundation, because we're going to revisit some of these as we move forward. So. Okay, anything else? All right, have a great day. See you tomorrow. And I'll check with the other rooms, but yeah, if any other questions come up, feel free to send me a message through Remind. Okay.
Thank you.
Thank you. Have a good day, guys. Thank you.
Thank you so much.
Bye.
Thank you.
Thank you. Bye.